layers, at the bottommost layer, generally you'll have your operating system image. This is where various commands like ls and cp exist if you've got a whole operating system packaged inside your layer. Okay. On top of that, sorry, too many rectangles and it's not too easy to see which one is a rectangle, which one is just the space in between. On top of that, you might put in several very important but not critical to the operating system utilities. Okay, who uses like OpenSSL? Oh, yeah. So you might want to have your SSH libraries here. Okay, you might want to have other things that you would expect to be pretty much in most systems. Okay, you might have then another layer which contains your application that uses those libraries. Okay? And then you might have a final layer which contains the on-disk configuration files that are being used to configure that application for a specific purpose. Okay. All of these are packaged into a thing called an image. This image has an extra couple of pieces of information that's not actually part of the file system. It has basically the primary executable. When this image runs, it is going to run that primary executable. Now there is a detail here that is missing between the image and the process. And that is that real processes eventually change their file system. They write to something. And if all of your layers are immutable and cannot be modified, then this process couldn't do anything. So when it launches, there's an extra layer that is created. This is the read-write layer. Okay? And so, if someone saves a new, like you can log into this, and if someone saves a new copy of the config file, it doesn't change the config file in this layer. Instead, what it does is it writes the new copy of the config file up here. If this image gets redeployed on another machine, it won't get that new copy. Okay? If it wants to, say, remove a key utility, then it will write in the removal of some inode that's holding that utility, or the rewrite of the file system inode that's holding that utility. It won't actually remove the utility from the layer below, because these layers are immutable. But what you've done is you've lost your handle to that chunk of the file system. So that means that if you have a malicious attacker and they decide to, hey, I got in, I'll just rm-rf the whole thing. They don't wipe out your operating system, nor do they even wipe out the application or the configuration. You might have to relaunch another copy of your image. Okay? Likewise, if someone decides, you know, I got this really cool trick. It's a backdoored ls. Every time somebody LS's, it sends me a copy of etc password. Well, they can put their own ls in here. They have managed to compromise this one container, but they have not managed to compromise the operating system. Someone that's inside a different container would have a complete copy of this with its own different read-write layer, and since it doesn't have an ls that's blocking the access, because the layered file system, it reads sort of like from the top down. So an LS, if that wasn't there, it would read all the way down to the LS down here. If this config file wasn't here, it'd read all the way down to the config file right here. If somebody didn't remove, I don't know, the SSH libs, it would read all the way down to the SSH libs down here. It just reads according to its file system path until it finds the first layer that provides something from top to bottom. It's sort of like BSG jails on steroids. Okay? But the point is that this is how this layered file system works. It's very important for understanding Kubernetes security because Kubernetes security is based on top of Docker containers. And Docker containers all use this layered file system. Now, that's how you keep the operating system mostly secure. There's a second thing. What's the one file system that's always dynamic?
RAM memory?
What's that?
RAM?
Yeah, RAM is where you hold a lot of things, and you can hold file system information in it too. But the thing is that there's a file system. Who has ever had to look up their own process ID information? It's proc.
Proc, yeah.
You can't implement proc here. Because if you implement proc, proc has to be completely static and immutable. We all know that processes aren't static and immutable. So when this thing runs, there are a couple of places where it can reach down to things like proc, which creates a new problem. We said we wanted to keep this process unaware, not just unable to screw up the computer, but also unaware of the stuff on other people. Because like sometimes you can identify that the target is more valuable if you can just figure out what it's running. And then you can invest more time to attacking that target. So there are extensions in the Linux kernel to say, I want to launch a containerized proc entry. And when you do your PS listing inside this containerized proc entry, unlike what you would normally see, you will only see PID 0 and yourself. And if you do it in the operating system outside of this container, you'll see the listing of everything. Matter of fact, the ID inside proc, since IDs usually increase from 0 upwards, yourself will be ID 1. And so you'll have a ton of PID 1s if you go into each container and take a look. But if you step back out to the operating system and you take a look, you will see every one of those actually has a real PID that is not 1.
Right.
Well, unless you're, system D, then it would be.
Is this or is this similar to namespaces?
It's similar in the idea of namespaces. Namespaces, you create a name, and anything that could be defined could have a duplicate in another namespace. In the sense that your PID 1 is PID 1 in each one of these containers, it's like a namespace for processes, okay? In the sense that your files exist in the container and not necessarily in the operating system, it's like a namespace for your file, for all your file system modifications. But it's not a namespace because it misses one of the most important parts of a namespace, which is namespaces have a name. So you can identify which one you have. In this case, this is just your view of the world. Okay? So, what's that? Is it an Adam Sandler movie? I can't remember. What's the movie where the guy has been living in a bubble his entire life?
Bubble Boy.
Nice try, but that's not the one I'm looking at. It's actually he's a part of a TV show and he just doesn't realize.
Truman Show.
Truman Show. Okay. So that's not a namespace. That is a virtual environment. He doesn't know another name for it except the world. Okay? And once he gets out of that world, he might realize that there are other worlds out there. Whereas a namespace would be like, you know, what is the customer that's in this filing cabinet? Or what is the customer that's in, there's always some way that you can tie a name to it so you can organize and you're aware that there's more than one. Okay? So that's the only differentiation there. So it's sort of almost, but just falls short because it doesn't have a name. All right. So this is how pods more or less are constrained by the operating system, or how I should say containers are constrained by the operating system. Who has ever heard of Docker? Okay, you don't know anything about it? You now know 90% of Docker.
Sweet.
There's also other tools that are not Docker, okay? For example, have you ever heard of Podman? It's the Linux popularized name that's mostly associated with Docker replacements. It's actually the command line tool that runs in front of a whole bunch of other services that all collectively replace Docker. But the point is that it's the same thing. It is a containerized environment. Okay, now that we've got containerized environments down, let's explain what Kubernetes is. Remember how we had virtualized networking? And we've got virtualized process spaces called containers. All right, connect those two together, and now you can have one container use a virtual network to communicate to another container that's also on the same virtual network. Okay? But what happens when you have two machines? When you have two machines, suddenly there become new needs. And so the new needs when you have two machines is that if you have something that's in one machine that's on a virtual network, it should be able to talk to the other machine, a pod on the same virtual network in the other machine. And the truth is that we know that this won't work without something extra simply because virtual networks aren't real networks and there is no real wire connecting the two.
Right.
Okay? So Kubernetes solves this with virtual networking that spans multiple machines. Okay? And it has an interface for this. I'm trying not to think of the container interface, which is called CNI. But it's got an interface that allows different pluggable ways of handling the virtualized networking between machines. And the entire idea here, I'll show you the simplest solution, which is we're going to use vBridge. Who knows about vBridge? Okay, there's a project called Open VLAN. Who's ever heard of that? Okay. Who has ever wished that they had a virtual switch to test something? Bingo. Open VLAN gives you exactly what you want. It actually started off with Open vSwitch was what it was called. If you would define a virtual network, it'd have a virtual switch. You'd define virtual NIC ports on the switch. You'd define virtual NIC ports on your, at the time, VMs. And then you would define virtual wires that would connect the two. I mean, it was like
Awesome.
hardcore virtualization for networking. Yes?
So would this be like bridging a VM?
Yes, very much so. One of the, yeah, actually it is CNI, Container Network Interface. One of the CNI plugins is one that binds to bridge control, BRCTL, vBridge control, I should say. Okay? So here you've got your physical machine, and here you've got your other physical machine. And inside here we'll have pod 1, and inside here we'll have pod 2, and pods are collections of containers that can be deployed at once. All right? So inside here we'll have container 1, and inside here we'll have container 2. And both of these are connected to, and I know this is horrible, but I need to use some sort of virtualization. So we'll say VNet1, and this one's contained to VNet1. Trying very purposefully to avoid saying VLAN, because that means a completely different thing in networking terminology. All right? And this one wants to ping this one. Let's pretend he already knows the IP address. Okay? This VNet1 is going to be implemented across your bridge, which is going to use your real networking, which is then going to route into the other VNet1. So if it does a ping, this bridge understands that for IP address, we'll say this is IP address 10 and this is IP address 20, and these are the VNet IP addresses. Okay, these are not the physical IP addresses. The physical IP addresses are on a completely different network, you know, 192, 168, whatever, 5 and 8. Okay? So when this one sees, hey, I am attempting to ping 20, there will be a routing rule in the bridge due to the magic of Open VLAN that says, oh, 20 is inside this machine. I will wrap it in a packet so it can get forwarded to this machine and handled by this machine's bridge, which will then unwrap it and put it on this VLAN, pretending that it originated in this machine because the LAN's in this machine. And then when this does a reply packet, the same set of routing rules will apply in the reverse to route it back over to this machine. Why did I cover this in detail? We're booting up node 3 and we're adding it to our Kubernetes cluster. It has its own bridge, and because someone wants to take this piece of hardware down for maintenance, they killed process 1. Kubernetes manages your pods for you, which means that it manages the containers within them. It will notice that it says this thing's supposed to be running, but then it will notice that it's not running. So it will go and it will find a suitable place to launch it somewhere in your cluster. When it launches it, let's say it picks this new node 3 because it's nice and empty. It's got plenty of spare capacity. Rewrites the 1, replaces the container 1 in there, rewires it up with IP address 20, and through the container native interface, reprograms all the bridges to forward to this node.
Oh. It does this automatically?
Yes.
Wow.
Now you can see why Kubernetes has value beyond Docker. Yes?
So I'm guessing this is similar to like AWS with their elastic IP addresses.
So the EKS service is actually Kubernetes. ECS is very similar to Kubernetes, but they built it in-house before they had like their whole Kubernetes, just direct binding. And then the elastic IP addresses, depending upon what you're using there, you might actually be using something that's very similar to a component in Kubernetes or not. Because you see, we're just talking all inside this virtual network. But elastic IP addresses, you can use it to route information from the real world into Kubernetes. I'm not into Kubernetes, into AWS services. All right? Kubernetes has something like that. And we'll get into that in a second. But right now, I want to make sure that people understand why it's cloud. It's cloud because it's not just virtualized machines. It's cloud because it's virtualized networking with virtualized machines. Or virtualized networking with virtualized processes. As long as you add in the extra virtualized networking, that's what makes it cloud. Whether you own the machines, someone else owns the machines, or something completely different. It's the most reliable definition of cloud I've found so far. All right, let's take a break before for questions. We're not going to get up and leave. Before we move on to the next chunk, which should be relatively short. So just keep filming because it won't stop. Who has questions at this point? Okay.
Do VPCs work in a similar way? Like a virtual private cloud? I don't know, like this is my concept from AWS because I work with it. I don't know if that's a concept that is also
So usually a virtual private cloud, okay, when you talk about a private cloud, it can mean one of two things. It can mean you're running all the cloud software on premises. So like you have your own Kubernetes installation, you can point and say these 12 boxes run our Kubernetes cluster. Okay, that's one kind of private cloud. A virtual private cloud is sometimes companies want to test a clone of that cloud where they're messing with cloud configuration prior to applying it to their really important cloud instance. In any type of cloud environment where you can run more than one cloud environment is where I'm used to using the term virtual cloud, because it means that you can easily roll out extra clouds. So like if you were to use, say, EKS 2 or 3 times instead of 2 or 3 Kubernetes clusters, that would be 2 or 3 different clouds inside of and those would be virtual clouds as opposed to like the one cloud that you actually have. If you do hardware deployments, it is possible to do hardware deployments where it is impossible to launch a second cloud on the hardware, depending upon how you configure it. Okay, and then that would not be a virtual cloud in my mind. But it's really kind of splitting hairs there because it means that you're talking about virtual in a particular context, when in reality, most of the services and items inside this cloud, wherever it's located, are virtual too. So you really need to make sure that you establish the context of what the virtual means when you attach virtual and cloud together. Private almost always means, though, that you're running cloud on hardware in your own data center. And public almost always means that you're running your cloud on hardware that is leased from somebody else's data center. Okay, you had a question too, I thought, or I thought your hand went up. Nope.
I have things rolling around in my mind, but I don't know if it's super valid right now.
Invalid questions are just as welcome.
You mentioned VLANs earlier. I was just curious because you have networking inside of the machines. If you can do VLANs specific to the pods or the instances, and kind of break them up that way.
The reason that I mentioned VLANs was so specifically I
couldn't
mention them.
Right, but it's kind of hitting.
But there are real hardware VLANs.
Correct.
Okay. Hardware VLANs are designed for an entirely different purpose.
Right.
Okay. Do you want to do a 1 minute on where hardware VLANs came from?
Mm-hmm. Sure.
I'm good.
All right. Way back in the day, and probably still today, Buildings were built with floors. So this is your typical 5-floor office building. And in some corner of that building is your network closeting. And your network closeting, generally the most unique characteristic of it is that they drilled through the floors so they can run cables up and down the floors. Okay? Otherwise, your network closet could be anywhere. If you're only on, if your entire company's on one floor, it doesn't really matter where your network closet is. All right? That means that they would put in switches in the network closet. And most of the ports in the switches would run through the floor to all of the pieces of hardware that they were attached to. And then you would have these trunk lines, usually redundant, usually higher speed, that would connect the floors together. And this allows you to have a computer down here, talk to a computer up there. It would first travel to the switch, then it would travel up the trunk line, then it would travel down the other line, and it would hit the other computer. This was great back when people only had to worry about getting the computers connected. One day, corporations started to say, gee, it's kind of funny. Bob down in sales has been trying to log into our accounting server for the past 15 minutes. You talk to Bob down in sales, he doesn't even realize it's the accounting server. He had one digit wrong on his IP address. He thinks he's been trying to log into the prospect system. And they're thinking, wait a second, we're a company. We have legal obligations and financial controls. And that includes not anybody in the building walking into the business systems and attempting to mess with the financials that we have to guarantee are correct and report it out to, NASDAQ for our entire, 401c filings to be valid. How do we stop Bob from getting there? And there's a lot of solutions. Firewalls aren't exactly the right solution for this because that would mean that you'd have to have the port number secret for the financial accounting software, which means that all the financial accountants would have to have this secret port number, which means it's not going to be a very good secret or anything else. So what they did is they said, what if we could take these switches and carve them up? Okay? And so instead of, because like the solution beforehand is, I'll buy an accounting switch, and our accountant's on this floor, and we'll run our own trunk lines for the accounting system. Okay? And someone said, no, this is going to be way too expensive. As soon as we do it for this way, we're going to have to do it again for this, and do it again for that. And so they said, I know. We'll go back to the internet protocol. We'll use one of those little extra fields that isn't used too much. We'll tag the packets with a virtual LAN identifier. And now, if you come in here on your switch port, your packet gets tagged with its VLAN ID. And it can travel up and down all the trunk switches at once, all the time. But before it leaves one of the ports to go out to the actual end computer, if that VLAN ID isn't the one on the exit port, it gets dropped. And so now you have a kind of security that allows you to simulate, yeah, actually we just stood up our own private accounting network. So that's why you have to be careful when you talk about VLANs, because that's what everybody's going to think about. because that's where the terminology is. That's the reason why you only get 256 VLANs in subsystems, 128 in older systems, and why the rules are so bizarre for VLANs, because it has nothing to do with virtual networking. Well, not nothing. It has nothing to do with the kind of virtual networking we were talking about before. All right. So that was an excellent question, thank you. Any more? All right, since there are no more, we'll step into, we've got an idea of how the hardware is set up for networking for Kubernetes. Now we need to understand how Kubernetes works from an API point of view. So you have this thing called the control plane. Who's ever heard of control planes? Who has ever heard of control planes? I think you should raise your hand, because you were in the last class when we talked about control plane. All right. Control plane is where you issue your commands. Who's ever heard of a data plane? Who's ever used FTP? Thank God. At least I got a positive hit on something. FTP, you issue a command, right? And then it starts doing something with data, right? Hopefully.
Hopefully.
Okay. And you'll notice something's weird about FTP. And that is that when you talk to people about which ports you open, you say you have to have open. You say, I need this port open, and then I need this range of ports open. And all the network administrators go, oh my God, he's using FTP, you know? And the reason why you need this one specific port open is because anything that's issued on the FTP port, can somebody look it up for me so I just don't remember what the number was?
21?
21, okay, thank you. So anything issued on port 21 is a command. And anything issued on those dynamic ports is the data, the transfer data. So FTP has a control plane and a data plane. Okay? Who's ever used that really nifty baseboard software where you can like log in and reboot a computer without having to walk into the data center?
Like IPMI, or what do you mean?
Thank you, IPMI.
Okay. I was assuming that's what you're talking about.
Yeah. I'm assuming that's what I'm talking about too. But the IPMI, you have ability to bring up an IPMI client, and your information won't be tracked as part of communications between computers normally. It's a baseboard signal. It's a control plane signal. You can reboot computers. Involves a lot of expensive licenses, but generally speaking, it works pretty well. Who has ever heard of PyV and what do they call it? PyKVM.
That's what Edwin was talking about.
Okay, fantastic. PyKVM, you get a Raspberry Pi, all right? You wire a couple of the points from the GPIO header to the actual power buttons of the computers that you're dealing with. You wire a couple of other ports into like the USB, and lo and behold, you can boot up another computer because your Raspberry Pi can simulate the button press, okay? You can also then use the USB ports in order to do like a KVM session and to present the UI back somewhere else. And they even have, most of them have a use of the HDMI port. So you can do like an HDMI in case you don't have the ability to do KVM inside your computer. You can see everything. Point is that would be a control plane. What the computer does when it would be running afterwards is the data plane. It's just this concept of something controls the data plane. The Kubernetes API lives inside the control plane. It's a API that's restricted through access control lists to where not everybody can call it. You'd have to have configuration for it. You would have to have, key pairs that are accepted by its PKI system. Okay, and like as long as you've got the right X509 certificates and you've got the right client libraries installed, you can actually change Kubernetes. Okay, now Kubernetes API is changed all the time by a command called kubecontrol. So don't think that this API is somehow like 100% super secure. It's only as secure as you make it. But the point is that never, while two computers are sending some information, the bytes inside an FTP packet might just accidentally match up correctly, and somehow you're going to change your Kubernetes system because they're in different planes. So Kubernetes implements this control plane in one of its virtual networks. And it implements the data plane where all the computers talk to each other in another virtual network. Okay? And Kubernetes implements a flat networking structure across all your nodes that are inside, one environment. The way this control plane works is it uses a database called etcd. Who has ever heard of etcd? I know you've heard of some of these things. Your arm must be broken or something. Okay, so etcd. Who's ever heard of etcd's older cousin, Zookeeper?
Sounds vaguely familiar.
Sounds familiar too, yeah.
Yeah, it's like a big thing during the big data years. Basically, the idea is you have a database that stores items, but instead of just storing like an item in a machine, it stores items across a replica set of machines in such a way that it guarantees that either the item is properly stored and can be accessible in the same fashion through multiple machines, or it doesn't get stored at all. And there's a lot more that can be said about it because it's got some really interesting math behind it and things like that, but we're not going to discuss any of that. Point is etcd doesn't exist as one machine. Usually exists as 3 to 5. However many machines that you have inside your etcd cluster, you can function 100% as long as you have a majority. So that means that if you have 5 machines and 2 of them are down for maintenance, you're still functioning just fine. Okay? Point is this gives the fault tolerance in what's going to be the storage layer of Kubernetes configuration. So when you want to create something inside of Kubernetes, you use this command called kubecontrol. That's an L at the end. Some people like to call it kubectl. Some people like to call it all sorts of things. I will call it kubecontrol. If you need a translation, translate in your head. So kubecontrol basically allows you to do various things. And one of the most popular subcommands off of kubecontrol is create. So if I were to tell this control plane that there is a new machine that is supposed to join this Kubernetes cluster, it would be kubecontrol create node. And depending upon what this third thing is, there could be a lot of parameters afterwards. With a node, I'm sure you can imagine that you would have to say like what its IP address was, minimally. And trust me, a lot more. These parameters get very bulky to type. Okay, there's usually like options where you can say option, IP address, blah, 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 equals whatever. But 90% of the time, what you wind up doing is you wind up writing a YAML file. And so inside the YAML file, all Kubernetes YAML files have a certain structure to them, and that's because all the Kubernetes YAML files map to what Kubernetes calls objects. And the objects all have a certain amount of regular templating that makes them all the same when it comes time to stick them into etcd, or pull them out of etcd, or modify them in etcd. So every object starts off, well, it's not necessary to list it in this order, but it is highly advised, starts off with an API version. Okay, and so we'll just say like, who has ever done an API? Beautiful. Thank you. Okay, when you've done an API, it's great. You spend all your time, you get this API working, and then what happens? Usually around 3 to 5 years after the API's been released.
Change it, you change it.
Yeah, you need to change it. Most of the time you change it by doing what? The sanest thing you could possibly do. You add to it, right?
Yeah.
But every now and then, you need to not just add to it. You really need to change it. So that means that, like, maybe you said host name originally, and someone said, oh no, we can't use host name, we've got to use something else. We've got to, you know, because it's no longer deploying on one host, now it could be deploying in, you know, multiple hosts or something like that. And you'd be like, oh, well, we can't get rid of the host name, because if we get rid of the host name, we can't support everybody else that was using the API. And so now you need API v2. API version for every object tells it right off the bat which version this thing is. So every single thing you do with Kubernetes is already underneath the version system. Second thing, kind. This is Kubernetes type system. You've got a YAML file. YAML file doesn't describe anything in particular except just information, but if you're trying to bind it to an object, you want that object to have some sort of a type, so you don't accidentally pull out like a node configuration object and try to use it to configure a volume, or try to use it to configure a container or a pod or something. So Kubernetes has a type system, and I'm like 95% sure it's kind, but it could be something that I think it's kind, okay? Who's ever built an API and then wished that they had something else in it? But the problem is they didn't really need that something else for everybody. They just needed that something else for about 5 to 10% of the people who are using the API. Metadata. The most important field in metadata, name. Outside of metadata name, you can put anything else you want in there. You do have to put the name in there, but the point is you could put anything else you want in there. You could put in there build number. You could put in there the date that you created this thing. You could put in there who created this thing. It doesn't matter. It's a free form, have what you will, nest the tags as deep as you want, who cares, nobody cares, but name is used internally by Kubernetes to differentiate between the different kinds underneath an API version. Okay, so name is required. Then, depending upon what kind of an object it is, because unfortunately they were not 100% consistent, you have one of two fields that is required. You either have a data or a spec field. And they're trying to standardize on spec. It's the specification of the object. whatever you're going to declare about that object. Okay? And so this is the YAML file, or the YAML template, that basically would allow you to detail any item in Kubernetes. All right, let's see. Wake up my systems now. Okay, so who understands about the YAML file and how it ties to the Kubernetes objects?
I'm guessing it's kind of like a stack when it comes to like Terraform or CloudFormation, but for containers.
It's like a serialization of the configuration for something. It's like the configuration.
So like an image?
Sorry, I got too technical there. It is the configuration for something.
So it's like an image?
Remember we already used that word very specifically to talk about the Docker items. So there will be YAML files that discuss images, but this one's not an image. Here, let me copy it real quick. Okay. Do I need to make that bigger, you think? Let me make it a little bigger. Service account. Most people would call this a Unix user. But since Kubernetes is very often running services, it's called a service account. Because user is very vague, when you're dealing with services, it could be a user of the service, or it could be a person inside the computer, service account. This basically says that we're using version 1 of the Kubernetes API. You'll notice that this one, unlike this, doesn't have a qualifier. There are parts of the API that are core. There are parts of the API that are sort of like extension add-ons, partitioned into different controllers. The point is this is using the core one. It's a service account. And you'll notice that I'm saying, hey, we need an Edwin service account. All right? And this Edwin service account will have 2 roles. They're technically labels. All right? He's got a developer and an admin role. Kubernetes probably doesn't even know what this thing means. All right? Unless you're doing it specifically because you know that a controller in Kubernetes cares about that role. And the controllers will have documentation on which roles they care about. And I noticed that I've used the word controller about 5 times now, and I haven't told you what a controller is. So we'll get there. Just for right now, realize that this, when submitted, will create some virtual user inside of Kubernetes that's Edwin. And if I see it running on the PS tree, okay, well, it's not going to be the same user in the PS tree unless I have an Edwin on the base operating system. But if I go back into that virtualized proc tree, it'll be user Edwin. Okay? Now, I use the word controller multiple times, and I try to keep myself from using a term before I've introduced it and I've violated that speaking rule. Let's talk about what a controller is. Who has ever heard of control theory? Who has a thermostat at home? I was worried. Okay. How does a thermostat work? You haven't asked or said anything all night. Come on, tell us how a thermostat works. Your own words.
You set the thermostat for whatever you want, and if it's too hot, then it just turns on the AC until it gets close to that point and turns it off as it gets close enough to the point.
Right. Perfect. Of course, I can tell that you live in Houston because you never said anything about it being too cold. Point with the thermostat is you have a set point, right? And it has some value. Let's say 74 degrees Fahrenheit, of course. And then it has a measurement that it takes. And it compares these two and determines the delta. And based off of the information of this delta, it does something. Or it does nothing. Okay? If this delta is very low, it turns off the AC. Or makes sure that the AC stays turned on. If the delta is very high and it's like 86 inside, it turns on the AC. Some systems that are more sophisticated can turn on or AC. Some people have split systems, some people don't, whatever, it doesn't matter. Point is that this concept of take a measurement, all right, compare it to the value, and then use that loop for the decision point is a control circuit. The advantages of this is that you can basically set values, and then you can walk away and you can assume that the system will constantly try to navigate back to that value. I probably messed up the diagram, so you can all Google control theory later on, and then you can tell me how bad I botched that diagram, but the concept is correct. You set a value, and the system tries to figure out how to find its way to get to that value. Remember how I said that kube control stores this information in etcd? That's all kube control does most of the time. I mean, kube control's got some other things for like switching which cluster you're looking at and gathering a couple of items and formatting them nicely. But most of the time it doesn't actually perform any of the things that's inside of here. Instead, what you have is you have a small army of controllers. So in my example, where I created a service account, maybe I picked the wrong object because service accounts are not the perfect example. But the point is that there would be a service account controller theoretically if it was going to create the service account without a pod. It only creates service accounts with pods, unfortunately. But there would be a controller there that would say, hey, there's no Edwin service account. So I would go and say, you know what's needed? My nodes need updating information that there is now an Edwin service account. And so it would say something along the lines of, right into the node's configuration, that now that there's a new account called Edwin. And then the nodes, as they worry about whether or not they've got the right configuration and they pull over, they would see, oh, we need to reconfigure ourselves to make an account Edwin with some sort of UID. And then when they are done, they're storing their actual runtime information in there, which is getting compared again, and now I'll say, oh, there is no difference between what is needed and what is there. Now, I completely made that up. For service accounts, it doesn't work that way at all. But the concept of how this works is important. This is how it works for nearly every other kind of object. It's just service accounts are kind of created on the fly when the process comes up. So, let's talk about a different one. Let's talk about a namespace. Ooh, that may have been good for presenting, but it doesn't really make much command. All right, I just created a namespace in my Kubernetes cluster called EdDemo. How do I know it's there? I can get it. You can see that compared to all the other namespaces, my demo's been alive for 19 seconds. I know, it's not long for this world either. This is the description of my demo. Okay? It has a name. It has this label here, which was automatically created with my create namespace. You can see its status as active. And demos have a few things that I didn't specify, so it went with the same defaults. There's no resource quota on this. I launch as much as I can until I finally hit the resource quota on the actual hardware. There's no limit ranges, which means that there's basically, it's unconstrained. I gotta look up the formatting because it's been so long since I tried to pull the object format out. Okay, so it's dash. Oh. Can't describe it, you have to get it. If I need to, for some reason, describe this namespace in a file that I need to store and check in, this is its description. But you'll notice that this has a couple of things that won't stay the same if I try to re-import it. It's got a UID. Okay? UIDs, they're not supposed to be stable in certain circumstances. If I could export it out and then report it into another cluster and they both have the same UIDs, it would be a failure of what UIDs are supposed to do. They're supposed to be relatively unique well, actually, they're supposed to be really freaking unique in a lot of scenarios. So that means that if I tried to check this in with the UID, it would complain that I was like over specifying. Resource version, again, that's an internal construct, so Kubernetes can keep track in etcd, which version is the active version. This is not something that would be in there. So I can take this out to a file, all right? Course creation can't happen, all right? Let's give it a name. Kill the other ones. I don't really want to specify the finalizers, and the status is something, yeah, I've got to specify something. If I don't specify, okay, fine, I'll say Kubernetes can finalize it. That means Kubernetes will clean up certain things after I delete it. Kubernetes is responsible for the cleanup, okay? Okay, so I deleted it. You can see it's gone, right? 100% gone. All right. I'll just do it the old-fashioned way. Describe events. So because it's got this standardized YAML format, I can reference the file and say create all the stuff in this file. Because YAML allows you to do multiple items inside the same file, I can use the YAML file separator here, the YAML document separator, and I can create another one. Now this file has two namespaces in it. Watch the output. Created both of them. So this solves one of the biggest problems that people have in DevOps, which is, I deployed it. How do I redeploy it? Okay? Well, I only showed you with namespaces, but there are other Kubernetes objects. Let's talk about the most fundamental object now, the pod. We talked a lot about Docker containers. A pod is a collection of Docker containers that gets deployed as one unit. Pods have various features to them, okay? But the basic core element is it's a collection of Docker containers that get deployed as one unit. All right, so if you've got a process that needs to run with, well, let's say simplest pod is one of the web servers. All right, let's see. Okay, I need to do my homework a little bit better. I was trying to do it real snazzy on the fly and trying to get you to see something that I wanted to build up to. The point is that I did a Helm chart, which is sort of a templating system that fills out most of this information for you, based off of a values file, and I spent some time getting it debugged, and it works fine. So what I'm going to do is I'm going to install my Helm chart. Oh, okay, so I see it's already installed. So in that case, I'll need to launch the dashboard and show you it already deployed. This is an application that I just deployed into Kubernetes that provides me with a user interface that shows me most of what's going on in Kubernetes. It's called the Dashboard app. Over here, you've got a menu where you can select your various kinds of items. Over here, you have various graphs and charts describing the items. Here you can see that I have one deployment running. That's 100% of one deployment. Okay. And inside there, it has 2 pods, okay, and it has 1 replica set. We'll talk about what these items are, but we're not going to make this a tour of every different object in Kubernetes because there's far too many of them, all right? So a deployment is kind of an unusual idea that is comprised of other Kubernetes objects. When you deploy software, generally speaking, you don't want to shut down the old system and then turn on the new one. That creates an outage. So what Kubernetes has is they've got a service, which is kind of like a load balancer that's a little bit more intelligent. And the service routes requests to wherever in Kubernetes the freaking nodes are that have the back-end pods that handle the service. All right? And that usually means that you tie the service to what's called a replica set. And a replica set indicates that you have more than one replica of a particular pod. You can configure the number on the replica set up or down, say you want 5 replicas, 3 replicas, whatever, and it'll handle them in a load balanced fashion. As long as you've got a service whose spec matches the attributes of the replica set. So the service will know which replica set it's wired to. And the replica set knows which pods it's instantiating or tearing down. If through some strange magic, okay, maybe not so strange, let's just say you've decided you've over-provisioned on a particular service, and you want to tune it down. So you're going to take 5 replicas and tune it down to 3. All right? What will happen is the controller for the replica set will notice that you've got 5 replicas deployed, but the definition only says 3. And so it will start to look through the Kubernetes and decide which ones would be the best ones to kill. And it'll try to do so based off of various attributes like, gee, this node's pretty heavily loaded, and it's got one of them. Let's kill it with a little bit more priority than this other node that's got it. It ranks them all, it decides which one it kills, and then it kills one of them. Okay? And it does that slowly to bring things down to where you finally have 3. Meanwhile, while that's happening, your service is looking at your replica set. And it's noticing that these replicas are dropping off like flies. So your service is rewriting its routing rules to no longer route to the replicas that are gone. Okay? And all of that is called, is the way that Kubernetes really would like you to design your application. If it's one of these sort of horizontally scalable applications. But when you have a new version, you don't want to shut all of that down and then start a whole nother one on the next version. So what happens is there's a thing called the deployment. The deployment contains two of these setups. Or technically it contains one service still, but it contains two setups of replica sets. It has the old replica set and the new replica set. And what it'll do is it'll tune the old replica set down at the same time it tunes the new replica set up. And so there will be a small period of time where users might get routed to the new one while a person still has a connection to the old one. When all the connections to the old one are dead or gone or whatever, then it'll kill that one and then it'll stand up another new one, and it'll keep that balance to where you have roughly the same number of replicas all the time, but they are just different versions until finally everything's running on the new version. One of the advantages of this deployment object is that you can do things like, oh my gosh, we messed up, please bring back the old deployment. And then it'll start doing the same process but in reverse. Because, you know, obviously if I just shut everything down, then what would be the point? Is the idea is to do it seamlessly.
Right.
So here is a deployment, and you can see that inside this deployment, let's see, where's the service for this deployment? There's the service for the deployment. If we take a look at for the services deployment, you'll see that it is tied to a replica set somewhere. Okay, there's the selectors allow it to select other objects in the system. So this basically indicates that this is part of a Helm chart that I've deployed, and there is the name of the application. And apparently I'm having a hard time navigating this user interface because I never have used this user interface. But if I scroll down a bit, there's the ingress port. And there's the pods that are currently underneath this deployment. And so this is the pod. You'll notice that the pod has a very strange name. Okay, apparently I can't list it by that name, probably because of how I've got my system set up. But the point is that this is the pod. You can see it's using this much RAM. Over here, it's using this much CPU. If I kill this pod, I wonder if I have the ability to kill it through the UI. I might not. Then what will happen is we will see that it will be restarted.
Maybe on the top right.
I'm looking. Trash can? Sure you want to delete the pod? Yes. Okay. So, do we have an activity?
With CPU.
Yep, CPU went to nothing. And you'll notice that 25 seconds ago, we got another copy. So even if you do manage to somehow kill it, or a machine goes down or whatever, the system will try to self-correct itself into having it running. That's about the end of the very well-prepared part of my presentation, and the last part arguably wasn't as well prepared. But the point that I have is I think this gives you enough understanding of what Kubernetes does, a little bit of understanding of how it works underneath the covers, and without getting into even more details, you know, like talking about how you should structure your pods or how you should structure your applications to take advantage of it, that's really a good stopping point. So, cool.
Nice. Thank you.
Welcome. Who thinks this has some value? All right. Who wants to hear more about Kubernetes?
Yeah.
Is there something in particular that you want to hear about? It's a very wide net saying more about Kubernetes. It's like saying, I'd like to know more about this Amazon AWS thing.
Right, yeah.
So I have a quick question.
Sure.
Are pods like a container for like replicas of the same type, like the same replicas, or like what are pods exactly?
Okay, so replica sets decide how many of a certain pod you get. Replica sets contain templates. Okay, let me see if I can show, actually, is there a place here to, there's a place here to edit it. So you see, this is the YAML for the replica set, and you'll notice down inside this YAML, we can get to the right spot, there's the specification that says what is in this replica set. Okay, and you'll notice that it says there's one replica that should be permitted, but then you'll see that it has a template. And if we take a look at the information inside this template, it's pod information.
Okay, so I want to make a quick analogy. So basically, a pod would be like an EC2 instance, and then the replica set would be like an auto-scaling group.
Very similar to that, yes. Okay, in the mechanisms,
Yeah.
not in what they are.
Yeah.
Okay, because the pod is a collection of processes, not a collection of machines.
Yeah.
Okay, so if we take this replica here, and let's say we're going to configure it to be 3, and we'll update it. Okay, now if we go back over to pods, you'll see that our memory usage and our CPU usage is crawling because we just put in a couple of extra ones. So it's crawling up a little bit. All right? And if we take a look down here, you'll see that okay, none of them are launching because I have a networking problem with this particular system. All right, but the point is that this, oh, no, it says it's running. Okay, fine, it says it's running. How many of them do we have? Let's refresh. All right, none of them are actually launching because these are web server replica instances, and they're all trying to bind to port 80. And I already have something running on port 80, so I basically need to fix my networking to have it mapped properly to the virtual network, and then that way they can all launch their own port 80s and have them all mapped to something else. Okay. But the point is that you did see how you could like change the replica set, and it is very much like an auto-scaling group, except that in this case, it, depending upon how you define the replica set, it might auto-scale or it might not. You can say I want exactly this many replicas, you can say I want a minimum and a maximum of these, you can tie it to policies that basically indicate that, like, you know, on higher latency, you want to launch more of them. On higher load, you want to launch more of them. There's lots of things you can do with them. The pods themselves, they wind up containing the containers. Okay, so this is a pod. Let me see if I edit it. This is a test one that I ran pretty early on, and I apparently forgot to clean up. and here's the container inside this pod. It's called test. All right. And looks like it just runs an instance of Alpine Linux. And if I recall correctly, I just put a while loop in this one so it wouldn't shut down real fast. Where it was like, you know, while wait for a few years, do nothing, or sleep. But anyway, I don't remember what I put in this one. Obviously, I need to clean it up. So anyway, one of the advantages of pods is that you have these containers that are called the init containers. Let's say you need to fetch something before you start really doing work. Fetch a configuration from a secure system. Fetch a secure key from a secure system. Fetch a password to a database. All right? You can put that in an init container, and it won't start the regular containers until the init containers finish. Okay? Where would I store this password? It's a layered file system. You just write it into the file system. No one else can get it anyway. You know, because it's in the read-write layer.
So would that be kind of like like the run scripts that they have in services like Netlify, Firebase?
Except that those provide with the controls to start and stop things. These would just sort of be like the get my environment right portion of that control. It wouldn't actually have the start and the stop. The way that Kubernetes knows whether or not this is working is it'll take a look at a URL called your health checkpoint. And it'll come back with a health check status. And that'll tell it whether or not it's still initializing, or it's ready to process, or it's started, or it's dead, or whatever. And so if we go back here, let's see if I can at least find that part quickly so I don't bore too many people. Okay, apparently this one doesn't have one. Let me see if the other one does, even though the other one is not really running correctly. Yeah, liveness pro. So here, for this pod, in order to determine if it's alive, it'll do a health check request. It'll do an HTTP to that host on the HTTP port, which is whatever the HTTP port is defined inside that pod, because we can redefine it in order to keep collisions from happening. And as long as it gets back some sort of a response from this URL, it's alive. And if it's this one, as long as it gets back a response from that URL, it's healthy. And so you can have different states between alive and healthy. For example, if there's a system that needs to start up, it might be alive, but it might need to do a lot of internal work. It needs to cache a large amount of information out of a database, or process something in order to be ready to handle its first transaction. Then you would actually have the health check URIs for liveness and readiness be different. And one would report, yes, I'm alive, please do not try to restart me. And then the other one would report, I'm ready to start processing. Because what will happen is if this liveness probe doesn't respond within its failure threshold, then it'll say, something must have messed up on the Docker pod creation. I'll kill it and I'll launch another one. And so when you have like really slow to start up services, you gotta come up with these or else you kill them before they start up. Mount points are how you can get extra file systems mounted into your your layered file system thing. And a lot of those extra file systems are writable and persistent, depending upon how you set it up. You can actually, if you want to write to the actual OS disk, you actually create what's called a host path mount point, and then you can mount the directory that you're going to be able to write into. There's a couple of security considerations. Never mount the root directory writable, otherwise the entire point of the layered file system goes out the window and you can mess with the operating system. And never mount anything above, never mount anything that starts with bar log. Because there's a specific attack that you can do to steal other people's log files. And there's a way that you can configure the host path controller to just not let you do that, even if you put it in the config file. So there's after a while you get into Kubernetes specific security settings and things like that. Jobs are the kind of concept of like a batch job. Okay. Daemon sets are when you need one process for every node. Cron jobs are like a batch job triggered on a cron tab. Replication controllers are kind of a different spin on replication sets, different way of handling replication. Ingress is how you get into the cluster from outside. Services are host names that do load balancing. So, you know, if you've got two processes and they communicate to each other and you want to be able to auto-scale both of them, you create a service for one of them. The other process connects to the service. It doesn't connect to the other items directly. Config maps are how you can store extra bits of JSON or YAML inside the system. If you put your config file into a config map, then you can just simply say, oh, by the way, I want this config map to be launched with this thing, and they'll read the two and you'll be fine. Persistent volume claims, if you've got another system that's providing storage, but you do not, you're not creating it on the fly, you want to map to something that already exists. Let's say you've got a bunch of web servers that all serve up your company homepage, okay? Some people will just say that's got to exist inside a file system somewhere for one reason or another. We don't want to have to figure out about like redeploying a bunch of applications where it's compiled into each application. We just want it in a file system. They all serve off the same file system. Then it's a system like Ceph, which can provide the files regardless of where you are, would be an external storage system. And a persistent volume claim would be how you say, I want to interact with this external storage system to get this particular resource from this external storage system. And so you would deploy it saying, this has a persistent volume claim. It has a claim to a volume that persists after the pod is gone, okay? And when it launches up, the persistent volume claim will eventually get traded for a persistent volume that is mounted to the pod on a particular directory.
I guess if you have like huge files and you don't want to make an image that gets big like that. I'm trying to think of why somebody would want to do that.
Pretend you have an application that, let's just say it's designed a different way, okay? We're not going to say it's good or bad, it's just different, all right? And when someone logs in to, I don't know, start shopping on their shopping cart, it writes out a session to disk, okay? And that's important because you've got these, I don't know, sort of like predictive systems to try to see whether or not your shopping environment is good. And so you're going to read through these sessions and see how many of them complete with the shopping, with them actually going to purchase, and what they did in every one of them. But every one of those sessions is going to happen in a different pod because you're scaling. So they all need to write to somewhere. Well, you're smart enough to realize that maybe the session ID number would be, combined with your pod instance, would be a good key because they won't overwrite each other. But your back-end system, it needs to read all of this stuff out of a directory because that's just how it's written. So then you would have a Ceph directory, and you would store all these things in the Ceph directory. And even though you've got 5 instances with 5 persistent volume claims, they all back to the same actual persistent volume. And they're all just writing their own file. You see how that might work? Not saying it's a great example, but it's just an example of how you could use it. Persistent volume claims are just useful for storing information. And in Hadoop systems, if you want to do a persistent volume claim against a Hadoop system, then actually that probably would be how it works, because Hadoop systems excel at processing text files. Secrets are like config maps, except they have some protections to not show passwords to the console and various other things when you do things like list them out or print them. Storage classes are kind of this little special thing where if you need to map a new kind of persistent volume, let's say you have an NFS server, Ceph, and something else, and you need to have a plugin that basically tells Kubernetes how you're going to talk to the volume gets translated, how talking to the volume gets translated into commands to somewhere else. That's a storage class. It's like a volume driver. Cluster roles are effectively the names in the cluster. Cluster role bindings is effectively the permission system for tying capabilities to the roles. Events are, of course, what happened in the cluster. Namespaces we kind of talked about, most people understand. Networking policies are effectively what rules you can put on who can get to what. So you can say things like, because that entire networking layer was virtualized, you can say things like, yeah, we're going to open up a path between this system and this system. This system, anything that it goes to like this network is just going to be dropped. Whatever you want to do, you can basically write, your sort of virtualized firewall rules. Nodes are, of course, the machines in the cluster. Persistent volumes, we don't have any because we're not storing anything, and so we didn't ask for any of them through persistent volume claims or some other mechanism, but they would be places where you could store files that would last longer than your files. Role bindings are, again, like cluster role bindings provide you access to APIs. Roles and role bindings do the same thing, except it's all inside the data plane. So you've got like an API layer, and then you've got a data plane security layer. And then service accounts are the actual, names of the users within this virtualized environment that the processes will run as. And you can set up standard Unix permissions on those. So I said I wouldn't go through every one of the freaking resources, and I did. I'm still talking. And I would like to stop.
Okay.
Okay.
Thank you very much. Is there anything that people want to hear about specifically in the next class about Kubernetes?
Show us how to solve your networking issues.
As soon as I get it done, it's done.
I think it'd be interesting to watch the debug process.
For some, it would be. For some, it would be.
And what else is there to go over?
Because I mean, like, cause that's like.
Now the rest of it is just building skills using it and learning patterns on how to
Yeah,
deploy.
maybe you could do a demo where you try to post some simple web app.
So have you deployed one, or one that you can show as far as deploying?
Hmm?
Can you show it deploying an app through Kubernetes, like something semi-simple, as far as a structure of going through the process of deploying?
I almost went and tried to show it right now. I
Right.
will show it next time.
Yeah, but something.
Probably
like
what
that's-
we all
But
want.
it's really gonna be, if it's just the Kubernetes, it's really just a bunch of kube controllers.
Right, but showing that, but also kind of laying out a little bit more of best practices, because you said you didn't want to go into it, but maybe if you have time next week as well, kind of when you're doing it, like here are the better practices of how to do it as well. Because you said you didn't want to go into it, maybe if you have time next week as well. Here's what we're doing, and here's probably maybe a better way of doing it.
So the best practices on this items, I can touch on a few of the
Right.
highlights,
Touch on
which
highlights.
I'd be happy to.
Mhm.
But it's almost like best practices for code development. It's a very wide.
Right, yeah. No need to go into everything, but just, some basics.
Yeah.
What if there's like a lab? Is it true that like a lot of us would probably be, what we really want is to be able to build a Docker and Kube cluster on our own?
Yeah.
And so like if he tried to get us started on that and walk us through a simple
Setup.
exercise, then it would be a hands-on. We'd be able to see
Yeah, while he does
see
it.
those best practices while we're doing them. That's probably the best way we would learn something like
Right.
this.
Yeah, while you do it, we can kind of do it ourselves and kind of explain, this is why we're doing what we're doing, and here's probably
Yeah,
a good way of doing it.
exactly.
So I didn't mention it this time, okay? And I'm